Hello everyone! Today we're going to be talking about latent heat, which is the follow-up video to specific heat capacity. Today we're going to be talking about something I brushed over in very rapid detail in the last video, which is what happens when the phase of an object changes. For instance, when an ice block turns into water. Alright, so first of all, before even diving into what latent heat is, I want to discuss a little something about the difference between solids, liquids, and gases. And you already may be aware of the difference between solids, liquids, and gases, but just to highlight the key traits of each of these three. Solids, the atoms in solids are typically arranged in a nice and neat lattice. They don't move around all too much compared to each other. They're restricted in a certain sense, and these little red lines that I've drawn between these atoms, the atoms are represented by these little circles, are the bonds between each of those atoms. And these atoms aren't vibrating or moving nearly rapidly enough to break away from those bonds. Those bonds are strong enough to keep them in position. In comparison to liquids, so this is the solid case, in comparison to liquids, and let's take water as an example, the molecule of water, H2O, these molecules will be attracted to each other via hydrogen bonds because oxygen is slightly electronegative while hydrogen is slightly electropositive. And so these atoms will float around. They might have some kind of connection between each other and they'll slide over each other, but they're definitely not independent atoms, or molecules I should say. They tend to stick together, but they don't hold any rigid structure. So they might move around. This atom here might join a different structure somewhere else, this one a different structure somewhere else. But liquids are definitely not in a discrete lattice like a solid. Lastly, of course, gases, if it was basically particles are just whizzing around independently, and they might, who knows, the two might hit into each other, or they just might go about their own way. They definitely don't have any kind of bonding structure between them. They do their own thing. So those are the difference between solids, liquids, and gases. And I want to highlight the fact that in order to really shift from a solid to a liquid to a gas, we need to be looking at these bonds here, and then the non-existence of the bonds here. Basically, what happens is, in order to shift from a solid to a liquid, or from a liquid to a gas, we need to adjust the bonding structure between each of these molecules. For instance, for a solid to a liquid, we want to be able, if we want to turn a solid into a liquid, we need to energize these atoms enough such that they're so energetic those bonds break, or they're not sufficiently strong enough to hold those two atoms together in a perfect lattice, and so they end up becoming a liquid. And then if we wanted to turn a liquid into a gas, we would need to break this bond by giving the atoms enough energy so they could go about their own merry way independently, and so they'd end up turning into a gas. And vice versa, if we wanted to cool down a gas and turn it into a liquid, we need to end up taking away the energy from the molecules so that they can start to form these hydrogen bonds and be able to start forming some structure. And vice versa again, if we wanted to turn back into a solid, we would need to take away more energy from them again so that these stronger bonds can start taking effect. So as said previously, a typical example is solid water or ice melting down to liquid water and then vaporizing into water vapor, into a gaseous state. So we're going to use this kind of setup, or I should say, we're going to be using the idea of water changing its phases to give us an idea of what latent heat is, and to use this as a more relevant and somewhat familiar setting for us to do some problems in. So if you want to study how these phase transitions occur, let me first graph the following. So if I graph the temperature of an object, I'm going to graph it in degrees Celsius. I could do it in degree Kelvin, but it's okay. It's the difference in temperatures which we care about. If I have temperature on the vertical axis and heat, that's Q, measured in joules, on the horizontal axis, we'll be able to graph where we think the energy is going as the temperature of an object rises. So let's say we start with ice at negative 40 degrees, say at negative 40 degrees. And we start giving it some energy. We start giving it some of this energy here. Well, what's going to happen is naturally, or what we expect from the equation Q equals to mc delta T, that as we give it more energy, its temperature is going to rise, of course, because these two are going to remain constant. It doesn't matter how much mass we have, let's just say we have some constant amount of mass. So it's still going to start rising. It's going to start rising here. If you're curious as to the actual slope there, you could recognize that delta T equals to 1 over mc q. And so if you wanted to really find what this slope would look like for water or any substance, you could recognize that the gradient is 1 over the mass times the specific heat capacity, but that's irrelevant for the time being. So the object would definitely heat up and its temperature would rise. And let's say it rose to 0 degrees Celsius. Let's say we're dealing with ice here. We're dealing with ice. Let me get a different color. So here we're talking about ice, and it's heating. It's heating up. Now what's going to happen? Well, at 0 degrees Celsius, the ice is going to start to melt. That is the melting point of ice, and the melting point means that its bonds or its molecules are energetic enough that the bonds are starting to break, or they're not strong enough to hold the ice structure together. And so all the energy we feed into it is no longer going into raising the temperature of the object. All that energy is going into converting ice into water. So this here is a phase transition. This is a phase transition. And this particular phase transition is melting. Of course, if we're going this way, if we're going the other way, it would be freezing. So it's melting. So basically the energy is, instead of raising the temperature of the object, is going into adjusting the phase of the substance, namely turning it from a solid to a liquid. And let's keep going. Now we have liquid water, again at 0 degrees Celsius. So water can exist in two states at 0 degrees Celsius, as either a solid or a liquid. And then it rises again, and let's say it gets to 100 degrees. This is obviously not to scale. It gets to 100 degrees. And now what is it going to do? Well, it's going to convert phase again. At 100 degrees, it's going to take some energy to convert it from a liquid to a gas. Here. Let me draw a little bit straighter. So just to be precise here, it is liquid water that is also heating if we're going from left to right. And then here we have another phase transition. Apologies for my bad handwriting. Phase transition. And this here is boiling. Now we have some technical terms for melting and boiling. In physics, we typically refer to the phase transition as fusion, and this phase transition here as vaporization. Okay, so we have ice raising up to 0 degrees Celsius, converting phase, turning it into a liquid, heating up again, converting phase into a gas along this line here, or energy is going into that, and then here the gas or the vapor is heating up again. So here, at these slopes, we can use our equation Q equals to mc delta T, but we can't really use it for these plateaus. Because the temperature isn't rising. It wouldn't make sense to use an equation with delta T in it if delta T is 0. What we use instead is a different formula. So it takes a certain amount of energy to break bonds. And this is where I want to introduce the concept of latent heat. So latent heat is typically referred by the letter L. And what it tells you is the amount of energy per kg to convert phase. Okay. Now, the thing is that we can say all good and well that the latent heat is the amount of energy per kg to convert phase, but which phase? Are we converting it from solid to liquid, in which case we're talking about the latent heat of fusion, typically denoted by LF, or are we talking about the phase transition from liquid to gas, in which we're talking about latent heat by vaporization, LV. Now, the good thing is that typically we have different values for LF and LV. So the latent heat of, the latent heat for water, is roughly 333,000 joules per kilogram, while the latent heat of vaporization for water is roughly, and I should probably write this in in scientific notation, 3.3 times 10 to the power of 5. For vaporization, the latent heat is 2.4 times 10 to the 6 joules per kg. So for every kg of water that I want to convert from liquid to gas, I would need to supply 2.4 times 10 to the power of 6 joules, which is quite a lot when you think about it. That is 2.4 times 10 to the power of 3 kilojoules, or 2,400 kilojoules per kg, just to convert it from liquid to gas. So it takes quite a lot of heat in order to do so, a lot of energy in order to do so. And so from this graph, or from this kind of relationship, we can kind of have an idea of what the formula might look like to actually figure out the connection between heat, between mass, required to change phase. And here is the key formula. So, just to recap, matter requires energy to change its state. The latent heat is the amount of energy per kg of matter needed to change a solid to liquid, fusion, or a liquid to gas vaporization, or vice versa, from a liquid to a solid, or from a gas to a liquid. It is given by the equation Q equals to mL, which makes sense given that we saw that L is a measure of the amount of energy needed per unit mass. It makes sense that the units are exactly that. So this is the second equation. You could consider it the quote-unquote latent heat equation. If you want to know how much heat is required to turn a certain mass of a substance into a liquid or a gas, or vice versa, you can just take the mass and you multiply it by the latent heat of fusion or vaporization. And when you multiply those two numbers together, you get the energy or the heat required for that phase transition. So, just to see some examples of substances with different latent heats, I've got a little table here. So as you can see down the left here, we have the specific latent heat of fusion, or LF. Apologies for the slight blurriness. This tells you how much energy you require per kg to either turn a solid to a liquid, or a liquid back to, or how much energy you need to lose per kg to turn back from a liquid into a solid. So water, roughly 3.3 times 10 to the power of 5, as we saw before. And you notice that different substances have different latent heats. They also have different melting points, which is not connected directly to the latent heat. And on the right-hand side here, we have the specific latent heat of vaporization, LV. Notice for water, it is quite a lot higher. Right, even though this number is smaller, the power here is an order of magnitude higher. It is not always the case. You see for gold, it's actually lower. So for the graph of gold, it will look something more like this. Right, the latent heat of fusion is it takes far more energy than the latent heat of vaporization, which is an order of magnitude lower. So there are some examples. And so this can tell us really how much energy we need to melt a substance, or to vaporize a substance, or how much energy we need to lose to cool a substance into a liquid, or to cool it down further into a solid. So it can come in handy not just for industrial purposes of, maybe melting or hardening metals, but it also comes in quite handy if you're talking about steam engines or refrigeration. Those kind of problems where we need to know how much energy we need to remove from the system to cool it down enough, or how much energy we need to give into the system to make it hot enough for the object to turn into a liquid or to turn into a gas. So here's an example of two questions. So question 1, find the amount of heat that it would take to melt a 1.2 kilogram block of aluminium sitting at 0 degrees Celsius. So we want to find the heat. We're told the mass, and it's sitting at 0 degrees Celsius. Okay. So we want to find Q equals to mLV. F. We want to find the latent heat of fusion because we're converting from a solid to a liquid. The mass is 1.2, and we multiply that by the latent heat of fusion of aluminium. And we look on this graph here, the latent heat of fusion is 6.6 times 10 to the power of 5 times 10 to the power of 5. And so we would get, let me just bust out my calculator. We would get 7.92 times 10 to the power of 5 joules. That's how much energy you need to melt a 1.2 kilogram block of aluminium. Pretty neat. Okay, let's have a look at the second question. 600 grams of some particular substance uses 660 kilojoules to melt. Find its latent heat of fusion and hence what substance it is. Okay, so we're given Q this time. We're given mass. We want to find latent heat, so we want to find L. And we're told it's LF in this case. So Q equals to MLF. So that means 660,000, so I attach 3 zeros, equals to 0.6, because mass is measured in kilograms, multiplied by L, F. If I then divide both sides by 0.6, I will find that my answer will be 1.1 times 10 to the power of 6 joules per kg. And that looks a lot like gold to me. So this substance here is gold. Lastly, we have a more involved question where we're going to combine specific heat capacity and latent heat into one. So the question is, a 250 gram cup of water is heated from 20 degrees Celsius to 120 degrees Celsius. The specific heat capacity of liquid water is 4,200 joules per Kelvin per kilogram, or joules per kilogram per Kelvin. The specific heat capacity of gaseous water is 2,000 joules per kilogram per Kelvin, and its latent heat of vaporization is 22.5 times 10 to the power of 5 joules per kilogram. Our task is to find the amount of heat required to bring the water from 20 degrees Celsius to 120 degrees Celsius. Now this question can look a bit overbearing with the amount of information there, but let's think about this. If we want to bring a substance from 20 degrees Celsius up to 120 degrees Celsius, we first have to take the substance, which is water, from 20 degrees liquid water to 100 degrees liquid water. We then need to convert it from 100 degrees liquid water to 100 degrees steam or water vapor. Right? So this is now 100 degrees. We go from 100 degrees liquid to 100 degrees gas. We then need to do a third step and find how much energy we need to take it from 100 degrees gas to 120 degrees gas, right? So it comes in 3 stages: stage 1, stage 2, stage 3. So let's have a look at stage 1. So to heat it from 20 degrees to 100 degrees Celsius, we want to use a classic Q equals to MC delta T. And so this will be the mass, which is 0.25, multiplied by the specific heat, which is 4,200. It's not exactly this number. Multiplied by the difference in temperatures. So the difference in temperatures here is 80 degrees. 80 degrees. And if we plug those numbers in, we'll get a value for the heat required to shift from 20 degrees to 100 degrees Celsius. So it's 84,000 joules, or 84 kilojoules. All right, now the second step is to find the amount of energy it takes to convert from 100 degrees liquid to 100 degrees gas, given that we have a mass of 250 grams of water. So for this, we can't use MC delta T. We have to use Q equals to MLV, where we use a latent heat of vaporization because we're converting from from a liquid to a gas. So this is 0.25, that's the mass that we have, multiplied by the latent heat of vaporization, which we're told is 22.5 times 10 to the 5 joules per kilogram. And if I quickly compute this, this gets us to approximately 5.63 times 10 to the 5 joules. Or if you want to write it out, expanded, 563,000 joules. 563,000 joules. So quite a lot more energy is used in just converting that liquid to a gas than it takes to raise it by a total of 80 degrees. That's quite a lot. And now we want to lastly find the specific heat, or sorry, not specific heat, the heat required to raise the gaseous water by 20 degrees. So we're going to take 0.25, multiply it by the specific heat capacity of gaseous water, which is 2000, and multiply it by the difference in temperature. So it's at 100 degrees, we want to raise it up by 20, and we will then get times 2000 times 20, 10,000. Makes sense, 10,000 joules. So each of these three stages, we now found the energy required for each of them. So the total amount of energy required is just the energy from each stage, Q1 plus Q2 plus Q3. So that's 84,000 plus 563,000 plus 10,000 equals to 657,000 joules, or 657 kilojoules worth of energy to convert from 20 degrees liquid water to 120 degrees water vapor. And there you have it. There is an overview of latent heat.